Okay. We have proven that this triangle is congruent to that triangle because of side angle side. And everyone was comfortable with that, and that's good. We then use that information that this triangle is congruent to this triangle. We use that information to say that this angle is congruent to that angle because they're corresponding. What about the other corresponding parts? Well, isn't that segment corresponding congruent to that segment because of CPCTC? Acknowledging that segment's congruent to that segment, what can we say is true about the other diagonal? Okay, I see where you're going. I like that. Acknowledging that they're not only perpendicular, but it's also bisecting it. For item 5, or whatever number we're on, you can just write that one diagonal is being bisected. Only one of the diagonals is being bisected. You can identify that diagonal, which one is being bisected. We know that this was given to us. That is congruent to that, and this is congruent to that. So we know that when we drew in this horizontal diagonal, segment KT, that created two congruent triangles. However, when we draw in this diagonal, and just that diagonal alone, what kind of triangles is that creating? Are they congruent? They're definitely not congruent, but one property that is true about them both is what, Luke?
They're isosceles.
They're both isosceles. So, if you want to add a little bit to that property about the diagonal that's being bisected, the diagonal that's being bisected will always form two isosceles triangles when being drawn in. So the diagonal that's being bisected, that is being cut in half, cut into two congruent parts, is the diagonal that creates two isosceles triangles when drawn in. Cool. So be aware of that when you draw in this diagonal, it creates two isosceles triangles. And you can use that knowledge to help you figure out missing angle measures. For instance, if this is an isosceles triangle, then I know that in all isosceles triangles, the base angles are congruent. So this is congruent to that. I can also say that since this is an isosceles triangle, that this angle is congruent to that angle. So it doesn't just stop at these new properties. We're going to be using all the stuff we learned last semester about all these triangles and isosceles triangles and base angle theorems and all that fun stuff. Cool. The next part. Number 3, item 3. It says, Mr. Cortez says that the diagonals of a kite bisect each other. Is he correct? Yes or no? Do the diagonals bisect each other? They do not bisect each other. Will that ever happen in a kite? No. So it says to convince yourself or support your answer with a valid argument. We didn't talk about this too much when we were dealing with congruent triangles, but if I can prove that triangle is congruent to that triangle, that doesn't look anything, sorry. Anyways, let's just pretend that those triangles are congruent. Yeah, if we can prove they're congruent, then yes, we know the 6 parts that make it up, the 3 interior angles and the 3 sides. Yeah, those are all corresponding and congruent. And we didn't talk about this that much, but it should just make sense to us. That if I were to draw in one of these triangles' altitudes, and then I drew in the corresponding altitude in the other triangle that is congruent, wouldn't it make sense that this corresponding altitude is going to be congruent to this corresponding altitude? since these triangles are the same exact size, same exact shape. And so that's why the theorem is CPCTC. It's corresponding parts. It doesn't just stop at the interior angles and the three sides. It goes on. The medians, the altitude, perpendicular bisectors, all those segments that we learned last semester. As long as you're talking about the corresponding ones, those special segments will also be congruent. So the reason I say that is because if I look at these two isosceles triangles, clearly they're not congruent. They will never be congruent because by the definition of a kite, you need to have two distinct pairs of congruent consecutive sides. If you have, so if these triangles will never ever be congruent, and I draw in that other diagonal, and this was point D, if I'm just strictly looking at the larger isosceles triangle, I could call this segment DT, I could call it the altitude. It's one of the triangle's altitudes, correct? Goes from vertex to opposite side. Then I can also look at this, the smaller isosceles triangle, segment KD. That too is a altitude of this triangle. But they're actually corresponding because both of these altitudes are starting at the vertex angle. Remember, in an isosceles triangle, the vertex angle is the one being formed by the legs. So it's coming from vertex angle to the opposite side and being perpendicular. So these are corresponding. Since those triangles will never be congruent, then that means that these altitudes will never be congruent because they're corresponding. So if the triangles can't be congruent, then those altitudes sure aren't going to be congruent. So that's just one explanation of why the diagonals do not bisect each other and will never bisect each other in a kite. Okay, I want you to answer number 4 and 5 with your neighbors. Number 4 is that's just a discussion, but number 5, however, is going to take some arithmetic. I want you to write out and figure out what the area of that kite would be. When it says in terms of the diagonals, that means they want you to use the variables. So the length of segment AC and the length of segment BD. They want you to use those variables. So you should be able to answer number 4 really quickly. However, number 5, that's probably going to take some discussion with your neighbors. All right, ready, go. So what it means by in terms of diagonals is like if I wanted to represent the area of this rectangle in terms of its base and height, that means I would replace the base. Yes, the object is segment AD, but if I'm plugging it into a formula, that means I'm talking about a numerical value. So the base is the length of segment AD. So whatever that length is, I'm going to be multiplying it to the length of the height, which is, the height is segment CD, but I'm plugging it into a formula. It's a numerical value, so I'm going to change the notation to the length of segment CD. That's what you're doing. Does anyone have the formula for a kite, or sorry, the area of a kite memorized? Okay, good. You shouldn't. So we can't just, so if you're trying to search for or remember what the area of a kite is, we haven't learned that yet. We don't have that memorized. But could you break this shape, this kite, up into polygons that you do have the area formula memorized? That's the ticket. That's what it's looking for. All right, so I'm hearing good discussions, and I like it, what I'm hearing. But remember, this is check your understanding in your textbook. Like, this is a homework problem. So we should be here. We should be able to answer this question. Because even though kites are new to you, this is just reasoning. This is just logic. How can I determine the area of this shape? So I know that the area, so capital A, I'm going to put sub K, so the area of the kite, I know that I can break it up into the area of two triangles. And so if I can find the area of this triangle, and then add it to the area of this triangle, then I'll have the whole shape. I'll have the area of the entire kite. Now, what do we know to be true about these two triangles? They're congruent. They're the exact same size and shape, therefore they're going to cover the same exact area. So the area of this kite really is just two of these congruent triangles, right? We okay? What's the area of all triangles? Base times height divided by 2, or same thing, 1/2 times base times height. Can we simplify this expression at all? Yes. What's 2 times 1/2? It's just 1. So the area of this kite is base times height. But remember, this is referring to these triangles. It's not referring to the base and height of the kite. Where these variables or these values are coming from is with respect to these triangles that are congruent. So, what is one of these triangles' base? Well, we want this entire triangle. So this entire base right now is the length of the entire of that shape. So AC. So I'm gonna, and again, notice my notation. We're talking about an equation. These numbers. So there's no line above it. This is the length of segment AC. That is my base. Well, the height, I need this. I need the height. How could I represent this distance with respect to, because we have to put it in terms of the diagonals. So I can't say, hey, this is intersection point E, and say the length of BE. That's not in terms of the diagonals. You made up a new segment. So rather than calling that segment BE, what could I say that is? It's 1/2 of segment BD. Because we know that if we draw in this other diagonal, it's going to be perpendicular. And we also know that that diagonal is being bisected. It's one of the things that we